Good morning, ladies and gentlemen. Welcome to my speech. My title is Cloud Password Shield, a secure cloud-based firewall against DDoS on authentication servers. At first, let me introduce some backgrounds of our work to you. With the advent of Internet of Things area, more and more devices are tightly connected to the Internet in our day-to-day life. However, the rapid growth on the number of insecure devices also aggravates the power and scale of DDoS attacks and stops legitimate users from accessing essential network service. These devices are vulnerable to malware, for example, backdoors and trojans, which infects them and turn them into bots. DDoS are usually launched from a set of remotely controlled devices infected by malwares. Today, dedicated malwares are designed by hackers to recruit a botnet, then disrupt the victim by flooded bad requests. Generally speaking, DDoS attacks aims to stop legitimate users from accessing a specific network service, which disrupts their connectivity or service by exhausting network or server resources. For example, bandwidth, CPU, memory, and disk I/O, and others. They can be organized to send a large amount of requests simultaneously and continuously, and renders that attack much disruptive and uneasy to recognize the attacker from others due to the use of counterfeit IP addresses. The vulnerability roots from the fact that most password-based authentication services, like a Redis server, is powered by a regional database of user credentials. Such a centralized system cannot scale well in a large system. When coordinated attackers deliberately send incorrect login requests to the server at the same time, the database will exhaust its I/O resources and thus fail to respond to legitimate login requests. Unfortunately, existing DDoS mitigation services like Cloudflare can only limit the access rate of the login page at TCP/IP layer. This also affects the legitimate users. So this is our motivation. Let's define the coming bad request rate at lambda. Apparently, when the malicious traffic are involved, the lambda begins to increase and raises an alarm for a large DDoS attack when rising to some certain level. Upon this definition, our goal is to find out a pre-screening mechanism such that, in the view of a server, when the lambda is large, the average response time of determining an item in the backend shall be lowered, so it's impossible to survive the heavy workload under a DDoS attack. And in the view of the entirety of the server and the pre-screener together, when the lambda is small, the overall average time of determining an item shall acceptably increase, preferably none, so limited overhead is involved during regular cases. And the last but not the least, the additional pre-screening mechanism shall not compromise the security level of the password hashing-based backend. This is our building block, a Bloom filter. A Bloom filter is a space-efficient probabilistic data structure conceived by Bloom in 1970 that is used to test whether an element is a member of a set. False positive matches are possible, but false negatives are not. In other words, a query returns either possibly in the set or definitely not. This is an example of a Bloom filter where there are three hashes representing the set X, Y, and Z. The colored arrows show the positions in the bit array that each set element is mapped to. The element W is not in the set X, Y, and Z because it hashes to one bit array positioning containing 0. So, this is our contributions. The first is the Bloom filter as a pre-screener. We propose a firewall model to provide DDoS resistance for password authentication servers and describe details of a password prescreener using a global Bloom filter, which supports regular demands of an authentication server, like setup, insertion, query, and deletion. The second is the KSSBF. It is a key-based secure solution for trusted firewall providers. If the firewall provider is trusted, it is applicable to preserve a private key and execute the encryption or decryption process. Upon this setting, we develop a key-based prescreening Bloom filter, which achieves semantic security against chosen password attacks. This solution holds an ideal performance so long as the privacy of the key holds. The third is the GSBF. It is a generically secure solution for non-trusted firewall providers. Once the firewall provider is non-trusted, it is no longer applicable to let it keep the sensitive data. In the security context, we develop a Bloom filter that is generically secure without relying on private key. We show that the false positives in a Bloom filter, which is commonly regarded harmful, can be counterintuitively beneficial against the offline attackers, even computationally unbounded ones, who try to benefit from the Bloom filter. To make it precisely, we propose and prove the theorem of F-squared background noise. We also prove, in the context of indistinguishability, the advantage of any attackers drops to zero exponentially with respect to the number of passwords inserted to the Bloom filter. This is an overview of a password hashing-based authentication service with KSSBF. The properties are shown in this slide. The first is it has almost no overhead in regular cases, and it is highly resistant against DDoS attacks. The third, it is semantically secure against chosen password attacks. It is a provable security, and you can see details in my paper. But in this design, the cloud server must be trusted to keep privacy of the key. The principle of this design is, when there comes a password from the front end, our firewall behaves like a layer between the front end and the back end. When there comes a password, the firewall server with a private key behaves like a trapdoor generator. It generates a trapdoor with the coming password and its private key and write it into the Bloom filter at the front end. And when there comes an authentication request, the server also generates the trapdoor with the password and check it into the Bloom filter and only send the return true ones to the backend. And this is the GSBF. It is a generically secure solution for non-trusted cloud servers. Although the performance of KSSBF is regarded highly satisfactory, it relies on a trusted firewall provider to keep privacy of the key. Once a trusted environment to preserve the key no longer exists or revealed to be insecure, the Bloom filter turns out to be exploitable to attackers and in turn breaks the security of this scenario. Here, we will discuss the case when firewall providers are deemed untrusted. For example, run by a third-party enterprise. Apparently, it is not applicable to authorize the key or the password list to a non-trusted third party. Our solution is to design a Bloom filter that is regarded unprofitable unconditionally, so it is able to undertake the heavy workloads from the protected servers in an untrusted environment. So there are two layers of security in this GSBF. The first is nothing to gain, and the second is the F-square background noise on the indistinguishability. Both of them are provable security of our design, and you may see the details in my paper if you are interested. So let's come to the experimental part. This is the performance metrics of our design. The overall size of the Bloom filter is set to 1 MB, and 3 widely used uniform string hashes, that is BKDR, EK, and PJW, are employed. And let the lambda denote the bit request rate of an incoming login request flow, and F denote the false positive rate of a Bloom filter. As shown in the table, there are 4 possible outcomes from the prescreener, denoted by A to D. According to the definition of the lambda, the desirable decision of positive and negative shall be 1 minus lambda and lambda. However, there exists a F of false positives among the negative ones, thus C equals to F lambda. Accordingly, A equals to lambda minus F lambda, and obviously B equals to 0 and D equals to 1 minus lambda. As I described, the overall size of the Bloom filter is set to 1 MB, and 3 widely used uniform string hashes, that is BKDR, EK, and PJW, are employed. As shown in the figure, the case when F equals to 0.005 corresponds to the KSSBF, and the remaining 3 correspond to the GSBF when with different false positive rates. Only results of A are shown in the figure, since B and D are constants, and the results of C are very alike to that of A. From the results, we can find the experimental results very matches to the theoretical values we expected. We also performed the peak value testing on the firewall model with synthetic data. 2 Bloom filters, one is of low FPR, and the other is for a moderately high FPR at 0.36, are initialized as comparison to cases without Bloom filters. The number of requests varies, is time dependent, and comes with a peak in the left part of this picture, which simulates at a one-time attack. Peaks of random values appear at the right part of this figure, which describes a concurrent attack. As shown in the picture, the firewall undertakes the heavy workload and remarkably mitigates the power of peak values arriving at the back end. So this is the end of my speech. Thank you for your time.